you very much for inviting me. So today we'll speak. Today we'll speak about a proposal for a new technique to search for hidden baryons. I call this interstellar scintillation. And so the first question is, where are the Milky Way hidden baryons? So we know that we should have hidden baryons in the Milky Way, and the first answer that we can say is just where it is not. It is not made of machos with mass smaller than 1,000 solar mass.
Sorry about this. Let's try going into full screen. And then sharing it from Zoom instead.
Is it all right? Yeah, the screen looked also strange to me.
Suspense is killing me.
Yeah, your screen sharing is paused. This is bad.
Sorry, technical issues. Yep, I see the window. I see your email, which has probably also not attended. Hopefully we don't get presenter viewing that anymore. Yes, we're good.
All right. Okay, thanks a lot for your assistance. So I just said that the hidden baryons, we know now that they are not made of machos with mass smaller than 1,000 solar mass. This is also a new result from just from a few months. It has been it's a complement that has been made by the combination of EROS and old ancient archaeological macho and EROS data, and we have now a new exclusion that expands to 1,000 solar mass. So this is this extension that you can see here. So, but it's not the question today. So the next question is where are these baryons? And the proposal is to measure the last unknown contribution of this baryonic hidden matter, which could be made of cold molecular hydrogen plus helium, 25% of mass of helium, which is always also very difficult to detect. So if this gas is cold, so around 10 K, then you do not expect any emission. So you have a perfectly transparent medium. Then, so that's why it's hard to detect. So the question is, so this gas will be in the thick disk or in the halo, and my question is, do anybody has an idea on the quantity of this gas? If you of the column density of this gas, so you imagine that you just flatten all the galaxy, and what would be, in your opinion, the quantity of the gas per square meter you expect in the galaxy? Has anybody an idea on this? It's not much. It's only 250 grams per square meter. So like a sheet of paper, a very big sheet of paper, that's the size of the galaxy, but that's all the mass of the galaxy. It's just a very big sheet of paper. So that's interesting to know. So, so it represents the equivalent, a column of 3 meters of hydrogen under normal conditions of pressure and temperature. The point is that these objects should be organized into a fractal structure, this is an old proposal from Feniger and Combs, 94. So then it should cover 1% of the sky with a 1% factor amplification, of magnification of this column density. So you expect 300 meters of hydrogen that cover about 1% of the sky. So these clumpuscles, this gas should refract light. This is perfectly classical. So I say that there is no emission, no absorption, but it has to refract light because it's an elementary process. This has the polarizability of the molecule. I will not go into the detail. This is really in the textbooks. You can find it. And what the most important number you have to know is that the supplement of phase when you cross a molecular hydrogen, when you cross 300 meters of hydrogen, is 80,000, about 80,000 cycles. Okay, so it means that if you have only variations of the medium, fluctuation of the medium, turbulence, at the level of 10 to the minus 6, it should be sufficient to produce contrasted wavefront distortions. Then this is the scheme. Okay, you do not see the upper part, but this is scintillation through a turbulent molecular gas. Here on the left, you have a source. This is put at a large distance, you have the screen. Then you have a plane wave for the light. The light is a plane wave when entering the screen. When it exits, when it goes out of the screen, you have a distorted wavelength. And the propagation of this wavelength is governed by the Fresnel diffraction, not the Fraunhofer, but the Fresnel diffraction. And then you expect a pattern with a typical size of spots that I will explain later. And this pattern moves with the relative velocity of the screen to relative velocity to the Earth. So then you have two typical radii that are to consider here. The first is called the diffraction radius, which characterizes the strength of the turbulence. And this is a separation such that you have a variation of 1 radian when you move from one RDIF. I will go later. I will develop a little bit more. And you have also a refraction radius, which is another radius. And this is, a very rough simulation of what you would expect. You would expect big spots covering the Earth, and at the typical speed, 200 kilometers per second of the screen. Okay, I have no time and not the correct material to do. Oh, yeah, that works.
Plastic sheet on the propagation of the laser beam.
Okay.
We observe large and variable spots in a relatively small area. Now, here is the effect of a structure with a finer granulation.
It's just a piece of rubber.
You see that the beam is more spread out in smaller spots.
So this was made only for the Zoom, but that's okay, it works. So, and that you see, this is just to convince you that you can learn a lot of a medium just by looking at the interference pattern. Okay, so the distance scales again. So the first distance scale is the diffusion radius, the diffusion or diffraction radius, as I said before. So that's the separation between. That's the distance that you have to move to have a variation, an average variation of 1 radian in the optical path for the light. So and this would correspond to a variation of column density of molecules of only 1.8 10 to the 18 molecules per square centimeter. This corresponds to a variation of 10 to the minus 6 if you consider the halo clumpuscules from the model of François Combe, or 10 to the minus 4 if you consider Bok globules, which are just nebula within our galaxy. And the formula that gives the diffraction radius is somewhat complicated. It has complicated exponent. This comes from the laws from the turbulence laws. Okay. So there is a refraction radius which is connected with the diffraction radius. Just to make a long story short, you can just see this example here. Here you have a strongly corrugated medium, and here you have lower and smaller waves, so that's just equivalent in reflection. It's not completely true, but it's a good proxy of what you expect. And you see that this refraction radius, which is the size of the region where most of the light comes, is larger when you have a smaller diffraction radius. Okay, you have another structure which can be related to the size of the structure, so global focusing or defocusing structures. And one of the very important size that plays a role here is the source size. The point is that what I showed before just is true for a point-like source. Unfortunately, a star is not a point source, it's an extended source. And then you have to consider what is called the spatial coherence of your interference here. So you have to make the convolution of the projected surface of the source times the image, the pure diffraction pattern for a point-like source. And this is really critical. This makes the contrast going down from 100% to only a few percent. So this is a full simulation on what happens if you use a realistic scintillation pattern. This is what you expect from a point source with the zoom here on this small region. So you see large spots and smaller spots in the zoom. This is what you expect by taking into account the chromaticity of the source, the width, so that's the temporal, the time coherence of the source. So you see, sorry, you see some and you have a factor of 2 in the modulation index. But you see that the most important effect is to take into account the extension of the source, because you have to make the convolution product of this surface times this image. So you end with only a few percent of contrast. And this figure, so here I show a pair of telescopes, so you see the curve. This is the true simulated light curve that you would expect when this pattern moves in front of the telescope. So it's characterized by two parameters, refraction time and a modulation index. So the first one, which is the characteristic time, it's related to the velocity of the relative velocity of the screen with respect to the line of sight. It's given by this formula. And what is important here is to realize that it's of the order of 5 minutes for reasonable parameters here, for standard parameters in the diffusion, for a diffusion radius of 1,000 kilometers, and for a typical velocity and distance, and for the wavelength of 1 micron. So it's 5 minutes. It's the order of magnitude of the time for the fluctuations of these curves. And the other parameter is the modulation index. As I said, it's limited by the size of the source, and but here it's what we expect from a theoretical estimate, and this is the series of realizations for the computing the modulation index. Each realization needs to generate a huge image, so that's why we don't have too many. And this is what you would expect, assuming so that would be the modulation index that we will see. We will see the sun, a star like the sun, located at 10 kiloparsecs through a cloud at 160 parsecs with a diffraction radius of 1,000 kilometers. Okay, so the signature of the scintillation, it's so you have first, it's a stochastic light curve. That's one of the difficulties, but it's not a random light curve, because you have some correlation between successive measurements. So you expect an autocorrelation. You have this characteristic time, which is a few minutes. The modulation index can be sometimes larger than 5% if you are lucky. And this modulation index decreases when you increase the star radius, and it also clearly depends on the cloud structure. So the signatures of such a and what is important also to notice is that there are some character signatures from a propagation effect. So there are some chromaticity effect that I will not insist on it, but the most interesting is that if you measure the same, if you observe the same star with two telescopes that are a few thousand kilometers apart, then you will see a small difference between the light curves, some decorrelation between the light curves. And this is, again, a simulation of this effect. So here you have a series of telescopes that are 2,000 kilometers far from each other. And this is the light curve seen by each telescope. And you see, for example, here you have a peak, and then you don't see anymore the peak. So you have some decorrelation that depends on the distance between the two telescopes. And this is a very strong signature of a propagation effect. There is no way, no intrinsic variability can mimic such an effect. Okay, so the chance to see such an event, I said that about maximum of 1% of the sky can be covered by such clouds. So the maximum of optical depth is 10 to the -2, so 1%. And then you have to multiply by the fraction of the events that you are able to detect. So that's this is widely unknown. It could be as slow as 10 to the -6, for example, for the microlensing, or even lower. So that's why we will need to monitor a very large number of stars to have chance to see this. So we did a test on the NTT telescope in infrared a few years ago, and we looked at stars behind this Bok globule in Ks, so you cannot see it because it's not K, but Ks you see through. And then we found two interesting candidates that oscillates that had stochastic variation during the two nights. And so we could extract some limits from these observations. First conclusion is that there is no overwhelming unexpected background, because we found only two candidates, probably wrong candidates, but just to say that there is no background, no strong background. So we were also able to put upper limits on scintillation probability. For example, here in the 2D plot, in the 2D diffusion radius, diffraction radius, and optical depth. So you see excluded regions for the three nebula that we have studied. And you read this plot as follows. Here, for example, you can say that less than 10% of the sky is covered by gas which has diffusion radius smaller than 60 kilometers. So we did the same exercise in the direction of the Small Magellanic Cloud, and where we were also again able to put an exclusion limit, and it starts to exclude some possibilities for the clumpuscle models from François Combe. Well, so what can we do with the Vera Rubin telescope with LSST? So I said that we need long series, few hours of short exposures, 15 seconds. That's perfect. And from the same wide field to have the largest possible number of stars. And we need also to precisely monitor the faint stars. So needs big telescope. That's just it means big telescope. So the proposal is to have a movie mode, to make a movie in one passband where we have the highest flux of photons. And so this could be done during the commissioning on the deep drilling. There is a proposal for the mini survey related to this science. So I am sure that other communities should be interested in this mode of observations. So the targets would be, if you look at the galactic plane behind visible nebulae, you say that you know that you have gas, then you could expect some signal, but you can also search for LMC and SMC to search for a blind search for invisible gas. So this is the prospect. This is now the most interesting for everybody here, is the prospect that you expect from the Vera Rubin telescope. No. Qu'est-ce que j'ai fait? Yeah. Okay. This is the contrast that you would the modulation index that you would expect as a function of the magnitude of the star. So this contrast depends on the magnitude of the star through the size of the star. So that's the size of the star, the relevant parameter. And you see here the contrast, that is a few percent to a few per mil. And here you have the precision, the photometric precision for one exposure LSST. So you see that if you look at source in the galactic plane through, for example, the Bog globule base 68, you will be sensitive to a diffusion radius of the order smaller than 4,000 kilometers. More interesting is in the galactic halo. In the galactic halo, you can go deeper. You can see less turbulent gas. Less turbulent means larger diffusion radius. And then you see that you can go down. You can go up to 60,000 kilometers diffusion radius. So, and now that my last transparency, that's the perspective. So to discover these scintillation effects, we will need a large diameter telescope because we need to monitor a large number of faint stars, wide field camera also, fast readout. That's perfect for Vera Rubin telescope. And this technique should be sensitive to the clumpuscules that have a structuration that induce relative column density fluctuation of the order of 10 to the minus 7 per change when you change by 1,000 kilometers in the transverse direction. So, so the proposal is that to do a movie during 1 or 2 nights, the second night is to confirm what you have seen the first night toward one of the Magellanic clouds, and that would provide an excellent sensitivity to the hidden halo gas. Thank you for your attention.
Thank you. Questions, Gotham?
So why have we not seen the signal with Kepler, which is looking towards Cygnus, so stars in the galactic plane behind a visible nebula, 30-second exposure, so around the thing goes deep enough certainly to see 30th mag, and it's a space telescope, so it doesn't even have the atmosphere. But
no, it's not big enough. You need really a very large flux, and you need sub percent. I made the computation that you need at least 2-meter telescope in the vacuum in the space to have enough light to be sensitive to the low modulation you have here. So it could be in principle possible with the new telescopes, but the field will be too small probably for this. So there is always something missing, you know, in the space. But that's a good question. Yeah.
More questions?
This is Simon Beer. So I wonder about calibrations in ground-based survey or data. So they rely on. I see a lot of covariances that when you see this on large patterns.
You mean between telescopes?
Between or with the same. So the Rubin telescope has calibrations in there that may actually wash this signal out, at least the default one.
You know, when you do consecutive measurements like this, you have slow drifts that you correct globally. So that's in the general scheme of the calibration, and I think there is absolutely no difficulty to do this at the sub-percent level with a very simple technique like this one, just normalizing global variations.
Yeah,
but
okay, I'm not as.
But this is probably a question that, if you are next week in Chicago, I am one of the person who will be in charge also of the calibration, so we can have more discussions.
Okay, yeah, thank you.
But I think that at this level, I have no. I'm very confident. You know, we did the same exercise with Eros, and now it's almost 25 to 30 years ago, and that has never been the main difficulty.
More questions? Yes.
Merci. Very, very naively, are there any other effects that could mimic as scintillation, like microlensing or anything else?
No, microlensing. No, it's a long time scale. You have the shape of the signal is is really you have something stochastic, you know, something stochastic but not random. It lasts, for example, if you consider a standard clumpuscule from François Corbes, it should last for a few months, for example. And but it's really scintillation at long time scale, but it's scintillation. It's not a global effect that lasts for a long time like microlensing. So, and also you have this connection, this difference. Well, if you are lucky enough to have two telescopes that are 8,000 kilometers apart, then you have some decorrelation between the light curves. There is a question that I have very often is about atmosphere. I think that's probably what you have in mind. Atmosphere is absolutely not a problem. I have, for example, a slide for this, because the atmosphere induces a speckle on Earth, which is of the order of a few centimeters. That's why you see stars blinking, because you see a fast change at the scale of a few centimeters, but not the planets, because of this smoothing of due to the stars. So if you have a scintillation pattern of a few centimeters, as soon as it enters a telescope, which is a few centimeters size, it's completely washed out the contrast. So you expect absolutely nothing from the atmosphere. And by the way, this has been measured also. There are measurements made on the polar star.
I will ask you the very quick last question. Do you need a specific filter, or is any filter good for the?
A filter that accepts the more light.
Okay.
That
so
would be
it
so
doesn't
G,
matter which band. Which
probably
wave.
G or R. I think
right.
G is the best probably for LSST.
Thank you very much. Let's thank Marc again. And the next talk is going to be by Adam Brazier and Bryce Cousins.